Hello everybody, in this video I'm going to be explaining what the second derivative test is, and then of course I'm going to show you how to find local maximum, minimum values, and inflection points on an open interval using the second derivative test. I'll also be explaining concavity and its place when being applied in the second derivative test. In the previous video I went over the first derivative test. If that's something that is of interest to you, I recommend watching that before this one. Let's jump right into it. A second derivative test is basically just using concavity to determine whether a critical point is a local max or min based on the second derivative. And what is concavity? Concavity just refers to the way a function's curve bends. If we look at this picture over here, this is basically just concavity. You either have concave up or you have concave down, where when it's concave up and it's a smiley face, you have a min at that critical point, and then when it's concave down, you have a max at that critical point. Therefore, the definition of our second derivative test: if f double prime of x is greater than 0, then the graph is concave up and you have a local min. If f double prime of x is less than 0, then the graph is concave down and you have a local max. If double prime of x equals 0, the test is inconclusive and you must use a first derivative test instead. So if we look at our graph here, this is going to be our two critical points, right? And if we remember our little test we just talked about, well, concavity, right? This is up. Wow, that was loud. Concavity, right? And then this is down. When it's up, you have a min. When it's down, you have a max at that point. That's all it's really talking about. When we look at this graph, we have concave up, therefore this point is our local min. Over here we have a frowny face, so we have concave down, and this is our local max. Basically, the second derivative test just helps us do this, but it also helps us find inflection points. Here on this graph, or function rather, where an inflection point is just a point of a curve at which change in the direction of curvature occurs. Therefore, at this pink point, it's changing, right? Because it's changing in direction, this would be our inflection point. Therefore, we're also going to be finding inflection points in these examples. I hope that makes sense. Let's jump right into this. We are given the following function. F of x equals x to the third power minus 6x squared plus 9x on the given interval. Remember, this is an open interval. Okay, therefore those endpoints that they're giving us aren't endpoints. They're not even included. It says find the local maximum / minimum values of the given function and its inflection points if it exists, right? Our first step is going to be finding the first derivative. And f prime of x is 3x to the second power minus 12x to the first power plus 9. Our second step is going to be setting her equal to 0 and factoring. I'm going to pull out the greatest common factor. Here, the greatest common factor is going to be 3. Now, we can factor this massive thing into two tinier ones, right? And to factor it, we just take 3 and we look at the factors of 3. And we ask ourselves, okay, when added or multiplied, this 1 and this 3, which one gives us this -4? And a -1 and a -3, when multiplied, is going to give us a +4, and when added is going to give us a -4, so therefore we're going to want the -1 and the -3 in here. Now we set each of these equal to 0, and this is going to give us our critical points. Therefore, our critical points are x equals 1 and 3. Does it fall within the given interval? Yes, it does. So we are good to keep going. Now this is called the second derivative test, so what do you think is going to happen next? We're going to find our second derivative. All right, if we take a look at our first derivative, we can figure out our second derivative. So f double prime of x is going to be 6x to the first power minus 12. That is our second derivative. To figure out whether our critical points are going to be relative max or mins, or local mins and maxes, however you'd like to say it, we need to plug in each one of our critical points into our second derivative. Let's do that now. Let's do our 1 first. So when we plug in 1 to our second derivative, we get 6 times 1 minus 12. That just gives us, what, a negative 6. Then when we plug in f double prime of 3, we get 6 times 3 minus 12. This is going to give us a positive 6, okay? And if we look at our definition, it says, if f double prime of x is greater than 0, then the graph is concave up. Well, 6 right here, well, that's greater than 0. Therefore, it's going to be concave up, and it's also going to make this our min. Our rel min, our local min, however you want to call it, it's going to be our min. Local min. Then this guy is less than 0, therefore it's going to be concave down. Sad face. Where we have our local max. Now that we have identified what our max and min is, we can find our ordered pair for these two values. In order to find our ordered pairs for these two values, we simply plug in 1 and 3 into our original function, and that's going to give us our ordered pair. Let's do that now. I'm going to do it in a different color because we kind of have a lot going on already on the screen. F of 1 equals, we're going to get 1 to the third power minus 6 times 1 to the second power plus 9 times 1. This is going to give us a 4. So f of 1 equals 4. I'm going to push this up. Therefore, our coordinate is going to be 1, 4. And again, this is our max, our local max, or rel max, where we had downwards. We had a concave down. Now let's do our 3. So we get 3 to the third power minus 6 times 3 to the second power plus 9 times 3. This is going to give us 0. Therefore, our coordinate is going to be 3, 0. And again, this is our local min, where we had a concave up. Okay, so far we have these answers. These are our critical points and their coordinates, right? Now let's go in and find our inflection points. So remember, our inflection points are just a point of a curve at which a change in the direction of a curvature occurs. In order to find our inflection points, this is where the second derivative really comes into play. We must take our second derivative, I'm going to do it in a different color, let's do it in blue. We must take our second derivative. Our second derivative was 6x minus 12. We must set it equal to 0 and find our x value. All right, so let's just do this like normal. We can either factor or we can go the other way with it. Either way is going to give us the same answer. So let's do it this way. We get 12 equals 6x. When we divide by 6, we get x equals 2. Okay, it's done. No, I wish. We need to make sure if this is actually an inflection point. Therefore, we have to draw a little number line, label our 2, and we must pick a number before and after this 2 so that we can figure out if it's actually an inflection point. If we get a change in signs from negative to positive when we plug in our 2 chosen values, then that's going to indicate that x equals 2 is an inflection point. Now let's just jump into it so you can see exactly what I'm talking about. I'm going to choose from the left side, I'm going to get as close as possible. Therefore, I'm going to choose a 1.9 to plug in. And then the right side, I'm going to choose 2.01 because I just want to get as close as possible. When we plug these into our second derivative, okay, let's see what we get. We get f double prime of 1.9 equals 6 times 1.9 minus 12. When we plug this into a calculator, it spits out a negative 0.6. We don't care to round, it doesn't really matter. All we care is if it's negative or positive. And we can see that this is a negative 0.6. Therefore, this side we have a negative. We can do our little dots if you'd like. Now let's do our other value that we've chosen. F double prime of 2.01 equals 6 times 2.01 minus 12. This is going to spit out 0.06, which is going to be positive, right? So on the right side, we have a positive. This shift in sign change indicates to us that this is indeed an inflection point. This guy is for sure an inflection point. If you are asked to find the coordinate of your inflection point, all you have to do is plug in x equals 2 into your original function. So we can do that right now. We can do this. So f of 2 equals, and our original function was x to the third power minus 6x to the second power plus 9x. Okay, so 2 to the third power is going to give you an 8. 2 to the second power is going to give you a 4. 6 times 4 is just 24 plus 9 times 2, which is 18, right? Then we can, we're kind of running out of room here. Let's see what we get here. We're going to get 26 minus 24. Therefore, f of 2 equals a positive 2. And our inflection point is at the coordinate 2, 2. So that wasn't too bad, right? That's really all we're going to be doing over and over again. Again, these are our critical points. These are our critical points coordinates, or points rather. And then this is our inflection point, and this is our inflection point's coordinates. Now, what would this look like graphically? Like, we have our points, but what would it look like? Is it actually adding up? So I'm going to zoom in and draw what this function would roughly look like. Roughly, once more roughly, it would look something like this, okay? Where this point is going to be a 3, this point is a 1, and here we would have, I believe it's a 4, right? Yes. All right. And if we look back at our points, it said that our local max was 1, 4. And would you look at that? When we look at the graph, that is our local max indeed. When we look at our local min, it says 3, 0. And would you look at this? that is. Our inflection point is what? Let's see. Our inflection point is 2, 2. And guess what? That would be right about here. And that is indeed where a point of a curve, of our curve, changes in direction of curvature, right? We just fact checked it, so we are all good. I hope this is translating. We're basically just doing everything like if we weren't given a graph of a function. Let's do this next one. These are all just repeated steps. We're just doing the same thing over and over again. If you want to pause the video and try it out yourself, feel free. Okay, let's jump into this. Our first step is to find the first derivative. Our first derivative is going to be 3x squared minus 6x to the first power minus 9. Then we're going to set our equal to 0, and I'm going to factor out the greatest common factor, which is going to be 3. That leaves us with x squared minus 2x minus 3. Then let's do this polynomial. We get x minus 3 and then x plus 1. Again, if we list out the factors of negative 3, we have to ask ourselves, what's going to give us, when added or subtracted, is going to give us this middle guy. And when negative 3 is added to 1, we get negative 2. And when negative 3 is multiplied to positive 1, we get a negative 3. Therefore, that's going to be our values in here. Right? We're going to set each one equal to 0. And we get x equals 3, x equals negative 1. All right. Now, we aren't given an interval, so we don't even have to check to see if it's in their interval. So we can assume here that it's going to be all real numbers. Now, we must plug our critical numbers into our second derivative to see what it spits out and determine its concavity, which once more will give us our min and our max. Let's do this right now. So f double prime of x is going to be what? It's going to give us 6x to the first power minus 6. That's pretty easy to work with, right? Now let's plug in both of our given values, f prime of x, oops, not f prime of x, f double prime of 3 is going to give us 6 times 3 minus 6, which is just 18 minus 6, which gives us a positive 12. Then we have f double prime of negative 1 equals 6 times negative 1 minus 6. This is going to give us a negative 12. If we look back upon our definition, it states the following. If f double prime of x is greater than 0, the graph is concave up, which is your min. Let's see. Is it greater than 0? Yes, that's going to be concave up, aka our local min. Now this is less than 0. We're going to have concave down, aka our local max. We have now used the second derivative test to identify our min and max. Something I like to clarify real quick, just in case you're wondering. So when we're finding our inflection points, you can't find your inflection points using your first derivative test. You can only use the second derivative test to find your inflection points. Just in case that's something you're wondering, because I remember when I learned this, that's what I was wondering. And no, you can only find your inflection points by using the second derivative test. Okay, let's keep going. Now, let's find our ordered pair for these guys. To find our ordered pair, we literally just plug in our critical points, which is 3 and 1, into our original function, f of, let's do 1 first, and some negative 1, silly. F of negative 1 equals negative 1 to the third power minus 3 times negative 1 to the second power minus 9 times negative 1 plus 16. This spits out a lovely 21. Therefore, our ordered pair is going to be -1, comma 21. And again, remember, this is our max. Now let's do 3. We have f of 3 equals 3 to the third power minus 3 times 3 to the second power minus 9 times 3 plus 16. This is going to spit out a -11. Therefore, our coordinate is going to be 3, comma, -11. And again, this is our local min. Now let's find our inflection points. Remember, to find our inflection points, we must set our second derivative equal to 0 and solve for our x values. Let's do that now. F double prime of x was 6x minus 6. We must set her equal to 0, and then we can just solve for x. We could do this 2 ways. We could just factor. We could do it like this. Whatever you want to do, you can do. It's going to give you the same freaking answer, though. And we get x equals 1. Again, we must draw a number line to figure out if we have a sign change, because that sign change is going to be an indicator to us that this is indeed an inflection point. We have 1 here. Now let's pick a number to the left and to the right. And of course, I'm going to get as close as possible. So I'm going to pick 0.9, and then I'm going to pick 1.1. Now let's see what our signs are going to be here. We're going to plug in 0.9 into our second derivative, right? Because it's called the second derivative test. Okay. And when we do this, we get 6 times 0.9 minus 6. When you plug this into a calculator, you will get a -0.6. And would you look at that? It's a negative. Therefore, on this side, we have a negative symbol. Now let's see what we get for our 1.1. We get 6 times 1.1 minus 6. When you plug this into a calculator, we get a 0.6, which is positive. Now, if we see, there is indeed a change in signs. Therefore, this is an inflection point. So we can proceed to find the matching pair for it. We have the x value, let's find the y value. And of course, to find the y value of this guy, we just need to plug him into our original function. Let's do that now. F of 1 equals, our original function was x to the third power minus 3x to the second power minus 9x plus 16. Oops, that doesn't really fit. Let's move it a little bit. Okay, does it fit now? Okay, a little bit better. Okay, let's put our 1 in there. Great. And this is going to give us a 5 when we plug that into a calculator. Therefore, our ordered pair is going to be 1, 5 as our inflection point and our only inflection point. Again, let's look back. These are our 2 critical points. We found their matching pairs. If you were asked to find the coordinates of your critical points, well, they're right here. And then when you're asked to find your inflection value or inflection point, you could list this or you can write the coordinate here. Now let's move on to example 3. This one is not so bad, but the next one is freaking awful. We're given an interval, again, an open interval, so we need to be careful. If we're looking at our function, we can see that x cannot equal 0 because then the whole thing will be defined. Otherwise, we are all good. And again, our interval is non-inclusive of that 0, so we're going to be fine. Our first step is finding the first derivative. Before I find that first derivative, I'm going to simplify this. And when we simplify this, we get x squared over x plus 1 over x. And again, this is completely legal because if you were to mush them together, you get the exact same thing. This can be simplified, right? that gives us just x plus 1 over x. And this is not in proper form so that we can take the derivative. Let's put that in proper form. To put it in proper form, we must take this x and bring it to the numerator. When we do that, we get x to the negative 1 power. Now we can take the derivative. The derivative of this function is going to be 1 plus negative 1 times x to the negative 1 power minus 1. I'm showing all the steps just in case you've never seen it before. So when simplified, it's just 1 minus x to the negative 2. And then this is not in proper form, so I'm going to put her in proper form. And proper form is going to be 1 over x to the second power. Okay, so our first derivative has now been found. Now we are just going to set this equal to 0, and we're going to try to find what our critical points are. Let's do this over here. 0 equals 1 minus 1 over x squared. Okay, let's do our algebra. We must subtract this 1. We get negative 1 equals negative 1 over x squared. And then you could do this a couple different ways. I'm just gonna cross multiply because again, there's a 1 down there, and then you can choose however you want your signs to go down. I'm gonna do this guy and this sign with this guy, and then I'm going to do these two. Negative 1 times negative x to the second power is going to give you x to the second power, and then 1 times 1 is just going to give you 1, okay? When we take the square root of each side, because again, there's a 2 here, it's not written, it's mostly implied, it cancels out this 2. Now we have x equals plus or minus the square root of 1, and the square root of 1 is just 1. Therefore, our critical values are going to be negative 1 and 1. However, we are given an interval. You have to remember that. Even if it's open, you still have to check. And in this interval that we are given, they say from 0 to infinity. Therefore, this guy, not a critical point. It's not included in the domain of our given function or the interval of our given function. Therefore, the only guy we care about is this x equals 1. Wow, all this work just to find our critical value. Okay, now let's find its matching coordinate, right? To do this, we're just going to plug her in to f of x, right? And this is going to give us what? 1 squared plus 1 over 1. And this is just, again, 1 to the second power is 1. 1 plus 1 is 2, and then we have the 1, so we get a 2. Our ordered pair for a critical point is 1, 2. Great. Now let's move on to finding our second derivative so we can figure out if this critical point is a min or a max. Our second derivative, well, let's write the first derivative first so we can take it directly. F prime of x we found out was 1 minus x to the negative second power. Therefore, f double prime of x is going to be what? Positive now. I'm going to show every step for this. Again, the derivative of a constant is going to be 0, so that's 0. We have minus, we bring our exponent to the front. There's technically a 1 here and we don't write it. So negative 1 times negative 2x to the negative 2 power minus 1. Therefore, f double prime of x equals a positive, again, because remember, 2 negatives multiplied equals positive. We get 2x to the negative third power, or rather, and this is not in proper form, so I'm going to put it in proper form. We get 2 over x to the third power. Now, we can figure out if our critical point is going to be a min or a max just by plugging it in. Let's plug it in. We get f double prime of 1 equals 2 over 1 to the third power, which is literally, oh wow, that's kind of ugly. Let's fix that. This is literally just 2 over 1, right? And that gives us 2. Okay, and 2 is greater than 0. So we use the definition of our second derivative test, right? 2 is greater than 0, so it concaves up, aka local min, right? Min. Okay, so this guy is a min. Now we can find out if we have an inflection point. Okay, let's do that. To find our inflection point, we must take our second derivative and we must equal it to 0. Our second derivative is 2 over x to the third power. We set that equal to 0. What do we get? Well, we get no solution, because no matter how you try to solve this, right, you're always going to get a whole number equaling another whole number in this particular case. Because let's say we tried to cross multiply, or we try to use the reciprocal. Like, we just can't. If we use the reciprocal here, what happens to our x value? It's gone, and we're just left with 0 equals 2. Therefore, no solution. Meaning we have no inflection points. Our given function is always concave up. Okay? Now this guy is a headache, a literal headache. Okay, let's jump right into it. Let's first find our first derivative, and we're going to have to use our quotient rule. We get the denominator times the derivative of the numerator minus the derivative of the denominator times the numerator, all over the denominator squared. Now let's simplify this. We get 2x to the third. Actually, do I want to do that? Yeah, let's do that. Okay, I'm just trying to look into the future real quick. So let's multiply it. We get 2x times x to the second power. That's going to be 2x to the third power plus 2x. Then we have minus what? We have 2x times x to the second power. That's going to give us 2x to the third power all over x squared plus 1. Again, all that is to the second power. Yes, okay, cool. So this cancels out perfectly, right? 2x to the third power minus 2x to the third power is just going to give you 0. And now we have 2x over x squared plus 1 squared. Now we must set our derivative equal to 0. But remember, we don't set the entire thing equal to 0, because if we did, then the whole thing would be undefined and we wouldn't have anything. Therefore, we only set the numerator equal to 0. So we're going to take our numerator equal to 0. We do that, we get x equals 0. Okay, we're not given an interval, therefore we don't have to worry about if it falls within a given interval. And for this one, we can assume that it's all real numbers, because our x squared in the denominator is going to spit out a positive no matter what negative answer you plug in there, right? And even if you put a 0, we still have that plus 1, so it's going to be fine. Okay, now that we have identified our critical point, we must plug it in to see what we get, right? So we plug it into our original function. And our original function is x squared over x squared plus 1. And that's just going to give us 0 over 1, which is literally just 0. Therefore, our critical point's coordinate is 0, 0. Good. All right. Now we must find our second derivative. Okay, this is where it becomes just painfully annoying. All right, let's keep going. Let's do her in a different color because we're going to have a lot going on here. Okay. Remember, this is our first derivative, and now we're going to take the second derivative of that. Okay, it goes the denominator times the derivative of the numerator minus the derivative of the denominator okay, times the numerator. All right, all over x squared plus 1 squared. And I'm assuming that you are familiar with the chain rule, okay? This is the chain rule that I just did here, right? This is all one thing, and then this was our numerator, okay? Now let's simplify this guy. F double prime of x equals, I'm gonna put the 2 in the front, so we get 2 times x squared plus 1, all to the second power, minus, and then we have this whole freaking mess in there. Let's see. I'm gonna do 2 times 2x times 2x, which is gonna give me 8x squared, and I'm gonna put that guy right in front of the x to the second power plus 1. Okay. And I put these brackets there because sometimes you can have like a really big expression inside the brackets, and then you have to make sure that this negative sign gets applied to everything inside. But in this case, there's not really much to do. We can just erase these brackets and the negative sign is going to fall perfectly, and it doesn't really need to get distributed because it's already part of that 8x squared. All right, let's write our denominator. And oops, I forgot to do one important thing. The denominator got squared again. So we actually now have x squared plus 1 to the 4th power, right? Because when you take the exponent of exponent, you just multiply the 2. So 2 times 2 is 4. Now we have x squared plus 1 all to the 4th power. Perfect. Okay. Now, if you notice something, we can factor out. We can factor out these guys and then cancel them. So let's do that now. We have f double prime of x equals, okay, let's be careful with what we're doing. We can pull out a 2, and we can pull out this whole little expression here by the multiple of 1, or multiplicity of 1, rather. So we get x squared plus 1 multiplicity. That's what we're pulling out. And when we pull this out, we're left with 1 minus 4x to the 2nd power, right? All over oh, did I make a mistake? Let's see. Oops, I did make a mistake. Okay, where did I make a mistake? Props to you if you could figure it out. Let's see what we did here. Okay, there's a lot going on. Let's see. 2 times x squared plus 1 squared, good, minus 8x squared times x squared plus 1, okay. No, we're good. Yeah, we're good. Okay. All is good and all is well, right? The only thing is we had pulled out 1 and we actually had 2. Okay, there we go. Found the mistake. It's gonna be fine. Okay, so we're actually left with x squared plus 1. There we go. Okay. And then we're left over here with 4x to the second power. Good. It's looking good. Over x squared plus 1 to the fourth power. Okay, this was a multiplicity of 1, so these can cancel out by one multiplicity. And we get f double prime of x equals 2 times x squared plus 1 minus 4x squared over x squared plus 1 to the third power. When we combine these like terms, we get f double prime of x equals 2 times 1 minus 3x squared all over x squared plus 1 to the third power. Now we can set our numerator equal to 0 because, again, we cannot set the whole thing equal to 0 because then we wouldn't get an inflection point. All right? When we do this, we get 0 equals 2 times 1 minus 3x squared. And we can literally just take this guy, set it equal to 0, right? Oops, that's not what I meant. Let's do 1 minus 3x squared equal it to 0. And we get what? Let's see. When we subtract 1 from each side, we get negative 3x squared equals negative 1. So divide this negative 3. These negatives cancel out, right? And we are left with x squared equals 1 over 3. When we take the square root of both, this cancels out the square root of 2. We get x equals plus or minus the square root of 1 over 3. Now let's take the square root of the numerator and the denominator separately. We get x equals plus or minus the square root of 1 is just going to be 1, right? So this guy is a 1. And the denominator is square root of 3. Like, you can't actually pull anything out of that, right? But it's bad form to leave in denominator, so we're going to put her in the numerator. To put her in the numerator, you literally just multiply the top and the bottom by her. All right? We get x equals plus or minus square root of 3 over. When these two guys get multiplied, you are left with a 3, right? Because 3 times 3 is 9. Then the square root of 9 is going to be 3. So the denominator is 3. Therefore, we have two possible inflection points, and x equals negative square root of 3 over 3, and then x equals square root of 3 over 3. Okay. Now, here's the most annoying part. Actually, no, that whole thing was pretty annoying. So we have to take our number line, and we have to mark these guys. Let's say we have our negative square root of 3 over 3 here. Then we have our positive square root of 3 over 3, which is basically just negative 0.577 and then positive 0.577. Now we need to pick a number as close as possible to the left and right side of this guy, and then the left and right side of this guy. Let's pick these numbers. Okay, the best option for this negative number would be a negative 0.6, and then before it would probably be a negative 0.5 would work best. So let's do our negative real quick. Remember, we're plugging these two values into our second derivative because it's called the second derivative test. We get f double prime of negative 0.6 equals, well, what was our second derivative? A freaking mess, right? 2, let's see. I don't even remember it. Okay, yeah, we're good. Okay, so this is our second derivative. Let's copy and paste her. Copy and paste so we can actually plug it in nicely. Okay. 1 minus 3 times negative 0.6 squared over negative 0.6 squared plus 1, all to third power. This is going to spit out negative 0.6. It's going to spit out what? It's going to spit out a negative 0.05. Wow, I can't even read my own handwriting. 565, I believe. I mean, the numbers don't even matter. It just matters if it's negative or positive. Over here, we have a negative value. Then f double prime of negative 0.5 is going to, I'm not going to write this whole thing out. Okay. If you put it into your calculator, if you put our second derivative into the calculator and then you plug in whatever value you want for x, it'll evaluate it as such. So when we plug in negative 0.5 into our second derivative, we should get 0.32, which is positive. So our sign over here is going to be positive. And then on our other inflection point, we have to plug in two numbers. Let's plug in a 0.5 and then let's plug in a positive 0.6. All right. So this guy for sure is an inflection point. We can see this sign change. Therefore, I'm going to erase all of this mess. Cut. Okay. Now let's plug in these points. When we plug in 0.5 into our second derivative, it spits out, it spits out a funky number. It's like 0.5 over 1.5625. And again, the numbers don't matter. It just matters if it's positive or negative. So over here we have it positive. Then f double prime of 0.6 is going to spit out what? It's going to spit out a negative 0.16 over like 1.8496. And again, this is going to give us a negative number. So we have that sign change, which means that this is indeed an inflection point. All right. Now that we have confirmed that, we can say that our inflection points are x equals negative or positive and positive square root of 3 over 3. Now to find its coordinate, right, we have to plug these guys into our original function. And both of these, when we plug either or, our negative or our positive, into our original function, we're going to get the same answer, right? Because if we remember, our original function was the following. F of x equals x squared over x squared plus 1. So both of these guys are going to get squared, so it's going to be positive. So we only really have to do this once. If you want to do it twice, if you're not seeing what I'm saying, go for it. Okay. It's going to look something like this. Let's just do 1, because again, it's going to give you the same number. Equals square root of 3 over 3 squared over square root of 3 over 3 squared plus 1. This is going to give you a 1 over 4. Again, if you plug it into the calculator, it'll spit it out. And we get a 1 over 4. And again, I'll just write it for the sake of writing it. Negative square root of 3 over 3. Plug it into the calculator, so we're going to get. It's going to give you the same number, right? This is going to give you the exact same thing, 1 over 4. Therefore, our inflection points are going to be negative square root of 3 over 3, comma 1 over 4, and square root of 3 over 3, comma 1 over 4. Okay, this was a trip. I hated this problem. I hated this problem so much, but I thought it would be really important to do it, even though it's just so disgusting. So these are inflection points. Right? And then, wow, we have so much stuff going on. This is our critical point. We only have one. And, oh, did we even figure out? Did we even figure out if it was a max or min? Okay, so when we had plugged in, I even forgot to say this. Wow, I just butchered this last problem. For this last problem, we got 1 CP, and this CP is our local min. If we were to graph our function, it would look something like this. Oh, actually, this is wrong. It should be, yeah, it looked like this. Okay. Where our CP is literally right here. It goes right through there. Okay. So that would be the min, and then this would be our inflection points if we're looking at it head on, right? Okay. So with the second derivative test, the definition here in the third quadrant, oh my god, in the third part says, if f double prime of x equals 0, the test is inconclusive, you must use the first derivative test instead. And that's when you would go and use the first derivative test, but I'm not going to go through that whole ordeal for that one little thing. If we draw it, we can see that this is for sure our min. Okay, but I wanted to make sure that we used all 3 cases. And again, if this were to happen, where it's you try to test it to see if it's a min or max and equals 0, then you have to go and use your first derivative test. Okay, so that is it for this video. This was bad. Like, the first 3 were good. This last one, I knew it was going to be awful. I just did not think I would butcher it this much. I might redo this video. But thanks for watching, and have a great rest of your day. In the next video, we're going to be going over integration. So if that's something that's interesting to you, stay tuned for that video. Bye. Thank you so much for watching.